Welcome everybody to this new session of our DI seminar. It's a pleasure to have today two speakers. We have Douglas Coates and Ian Melbourne. Thanks to them for being here with us today. So the first speaker will be Ian Melbourne from the University of Warwick. And this talk will be about mixing for infinite measure systems. Thank you.
Okay, well, thanks very much for the invitation. I've kind of avoided online talks, so this is the first online seminar I've ever given, so so I hope it goes okay. So yes, I'm going to give some kind of introductory stuff on infinite measure mixing and try to convince you that it actually makes sense. And then Doug was more specific and up to date. So the general setting is that that's not working. General setting is that there's a sigma finite okay, and the f, there's some map f going from x to x, and it's always going to be an ergodic measure preserving transformation. So that's the standing assumptions all the way through. And if mu was a probability measure, if mu of x equals 1, then mixing, the definition of mixing is perfectly well accepted. It just says that the measure of a intersect f to the minus a intersect f to the minus mb converges to the measure of a measure of b, and it should be for all a's and b's, and obviously the a's and b's should be measurable, but for all measurable sets a and b, this kind of intersection, the points in a, the n iterates, converges to the right proportions, measure of a times measure of b. And equivalently, because quite often it's better to talk about functions rather than sets, then equivalently, integral v w of f to the n d mu converges to integral v d mu integral w d mu for all v and w in, for instance, in L2. So that's all I have to say about finite measure mixing. And now I will try to, how do you move the next thing?
Yes.
Oh, okay, very good. So if I go too fast or if I miss out any definitions, just feel free to interrupt. But now I want to go on to the infinite measure case. So I'm still assuming, as before, that it's a sigma finite measure and f is measure preserving and ergodic. And the first thing we have to do is we also have to, f is conservative. So this is something that comes for free in the finite measure case, but it's just saying that Poincare recurrence holds. So if I take a set A, a positive measure, then I know it's going to intersect itself after the finite number of iterates. And that's going to happen infinitely often. So we assume it's conservative, and I also want to assume it's exact, which is just some technical condition. In the finite measure case, this would be stronger than mixing, but in the infinite measure case, we don't know what mixing is quite, so we just assume this stronger condition would make perfect sense for infinite measure systems, and is satisfied for all the examples we're interested in. And then there's some bad news, which is that there's a result of Hadjian and Kakutani from 64, and it says that probably wrong, that there exists a W that's measurable with positive finite measure, so I might as well suppose W has measure 1, such that if I look at the same thing as before, measure of W, I'm now taking both of the sets. So in this definition of mixing, we had two sets A and B. I'm just going to take them to be the same. So I take the measure of W intersect f to the minus n of W, and that ought to converge to the measure of W squared, which is 1. But in fact, it's equal to 0 infinitely often. So for infinitely many values of n, you get completely the wrong thing on the right-hand side. You get 0. And this is a kind of a general feature of infinite measure systems, that somehow things want to go to 0. This is worse than going to 0, because if it was converging to 0 at some rate, you might hope to find some that makes it converge to something nice. But because it's equal to zero infinitely often, you know there are no normalizing constants. So this is really bad. And this leads to three different opinions. There's kind of three different viewpoints on infinite measure mixing. And the first view is that there does not exist infinite measure mixing. And what I mean is that people took the Hajian-Kakutani example as saying that you can't come up with a reasonable definition of measure theoretic mixing. But that's one point of view. There's a different point of view that came up with somebody called Krickeberg in 1967, and he introduced some kind of mixing that he said that did make sense. And then more recently, Marco Lenci in 2010 with what's called global local mixing. So those are the kind of the three viewpoints. I like two of these viewpoints. I like the second one and the third one, but not the first one. So I'm going to talk about Krickeberg mixing and global local mixing. So that's where we are. So for the time being, I'm going to focus on Krickeberg mixing. And here the claim is that there should exist some sequence AN, just the positive numbers, AN converging, AN increasing to infinity, such that, so this is a thing that Hajian-Kakutani said we can't do, but what we want to do is function into a VW positive f to the ND mu is trying to go to zero, so we choose some fixed sequence A sub n that's going to infinity to compensate it. And we would like this to go to integral V, integral W. But we know by Hajian-Kakutani that we can't take any old V's and W's because they can't take the indicator function of that set that we had in their counting example. I can't take V and W to be this indicator function of this set capital W. That will fail. So we have to assume that V and W are nice. And certainly I should also assume they're contained in L1, so that the right-hand side makes sense. So that's Krickeberg mixing, roughly speaking, that one looks for a sequence A sub n, which is just defined in terms of the dynamics, and some nice large enough class of examples, V and W, things work once you multiply by these normalizing constants. Any questions so far? I don't know if I'm going too quickly or is this okay? All right, so to explain what nice means, it's best to look at some kind of examples. So I want to look at the intermittent map, and I'll start off with the simplest, or one of the simplest intermittent maps called the LSV map, Liverani Ciso-Vaienti from 1999. And this map kind of looks like that. It has one uniform expanding branch, but it also has a neutral fixed point at x equals 0. So the formula is f of x equals x1 plus 2 to the 1 over alpha, x to the 1 over alpha if x is positive, so that if x is less than a half, 2x minus 1 if x is bigger than a half. It's defined on the interval 0, 1. Here, alpha greater than 0 is a parameter. And somehow the idea is if alpha is really large, then this is almost an expanding map. But as alpha gets smaller and smaller, this map gets worse and worse. And it's well known that for alpha positive, there exists unique, absolutely continuous invariant measure up to scaling. And that mu of, called mu, and so this is the only measure I will consider in this talk, this unique, absolutely continuous invariant measure. And mu of x is equal to 1 if and only if mu of x is equal to infinity. It's infinity if and only if alpha is less than or equal So if alpha is bigger than 1, you get a nice absolutely continuous invariant probability measure, and it's mixing and everything. And otherwise, if alpha is less than equal to 1, you get an infinite measure, but it fits all the hypotheses that I mentioned. It's well known, it's certainly sigma finite, but it's also well known that it's a ergodic, conservative, exact. And so the question is, what kind of mixing properties does it have? And so it turns out that in this case, the normalizing constant should be log n in the borderline case. Remember, we want to find a sequence that converges to infinity to offset the fact that things want to go to 0. So if alpha equals 1, the borderline case, you just need to take log n. And otherwise, you need to multiply by something a bit bigger. So that's turns out to be the correct definitions for A. And then if alpha is between 0.5 and 1, then this is stuff I worked on with Dalia Tehesia in 2012. And we showed that if our nice functions are, we want V and W to have support in 0, 1. So you want them to, so by definition, the support is a compact set. So this is a support that's bounded away from the neutral fixed point at 0. And W should be bounded, but V needs to be bounded variation or holder, some kind of regularity class. So you have to make some regularity assumptions on the function V, and W just has to be n infinity and not seeing 0. Then an times integral V, so W composed of f to the n d mu, does indeed converge to integral V integral W. Okay, so this was the result. That's if we took this particular example and we took these kind of observables, V and W, that are supported away from the origin and V has some regularity, then you're okay. So that covered for technical reasons, we had to assume alpha bigger than 0.5 because we used some technique that in the probability theory was due to Gaussian and Lamperti, and their technique also only worked for alpha bigger than 0.5. And so in a certain general situation, alpha less than equal to 0.5 doesn't work. But Doney, in the probability theory literature, I did an extra hypothesis, and it turns out that Guzel could verify it. Also, turns out to be verified also for the LSV map. And so Guzel was able to cover the case alpha in 0, 1. So he didn't worry about the case alpha equals 1, but he was able to do alpha between 0 and 1 under this extra hypothesis in the probabilistic setting that turns out to be satisfied in the LSV map. So the whole range works. So you take the union of these two results, the whole range works, but then you can go a bit further because the Krickeberg mixing was just some nice class of observables, and maybe these ones are a bit too restrictive. They're kind of they don't see the origin. Maybe they should be allowed to decay a bit. Maybe they should be allowed to decay somewhat. This condition BV is, or holder, is obviously completely non-measure theoretic. So maybe one can get a bit closer to some measure theoretic class of observables. And so going back to the work with Tehesia in 2012, we were again, we took alpha between 0.5 and 1, and we still required that the support of W was away from the origin, and W was still in N infinity. But V could be made a lot more general. It could be made of the form U over H, where H is just the density, and U was Riemann integrable. So you can get rid of the no holder assumptions, no BV assumptions. This is a bit closer to being a measure theoretic kind of setting, but it had to be, for some strange reasons, the U has to be Riemann integrable. So that's the and again we know because of the Hajian-Kakutani example. You can't make it completely measurable. Okay, so that's what we did for the LSV map. But now I want to quickly mention there's a more general setup, because LSV is kind of special. So the more general setup was we have some inducing set Y contained in X that has positive finite measure. So we might as well suppose that measure of Y is equal to 1. In the case of LSV, we would take Y just to be the interval half 1, just the interval of the second branch that was uniformly expanding. And that's the one to be thinking of. Then you look at the first return time, tau goes from Y to the positive integers with is defined as being tau of Y is the infimum n greater such that f to the n of Y is in Y. So it's the first return time to the set Y. And this is well defined almost everywhere because of the Poincare recurrence, or which is not a theorem anymore, but it's a definition, the fact that we're assuming conservativity. So this is a completely general setup for conservative systems. You consider this kind of setup. And then you want two key assumptions. You want that the measure of tau greater than n is some slowly varying function divided by n to the alpha, where alpha again is some number between 0 and 1. Again, yeah, so that, you have that. And the other thing is that so elevated slowly varying functions is something converges to a constant or logarithms and stuff like that. But basically, it's asymptotically 1 over n to the alpha. And f, capital F, is defined to be f sub tau goes from Y to Y. So this is the first return map. This you start with a point, you have to do a number of iterates to get into Y. So you do little f that number of times, you get a map capital F that maps from Y to Y. And this should be mixing, and it should be what's known as Gibbs-Markov or AFU or other stuff. So as I don't want to define these things, but somehow the idea is that the capital F should be a nice map. The little f might have neutral fixed points. It has this infinite measure. The capital F is a nice probability preserving transformation, and it should be kind of uniformly expanding, probably with infinitely many branches, but uniformly expanding, good distortion, big images, that kind of property. So yeah, so the point is that for the LSV map, it is Gibbs-Markov and it is AFU. It's in both classes, and this is the kind of thing you want capital F to satisfy. And then the claim is that under these assumptions, everything that was in Grisel in 2011 and in my paper with Tihersia published in 2012, all of those results apply. So it applies in this kind of general setup. Any questions, or I'll keep plowing ahead? All right, so the thing is that this covers large classes of examples, including all intermittent maps. So there's a general theory of intermittent maps due to Rowlands-Weinmuller, and all of them have these kind of nice have this nice structure that the theorems apply. So an example, which I think Doug would focus on quite a lot in his, is an intermittent map with two neutral fixed points. Oops. So I've got a neutral fixed point at 0 and a neutral fixed point at 1. And so f of x near 0, f of x is some constant b1 x to the 1 plus 1 over alpha, same alpha as before. And that's as x goes to 0. And as x goes to 1, f of x minus x is asymptotically b2 of 1 minus x to the 1 plus 1 over alpha, where b1 and b2 are just any pair of positive numbers. So we're assuming that the things are equally sticky at the two neutral fixed points, but it's not symmetric, with the b1s and b2 do not have to be the same. And then the y, it turns out that there's two, you can have there's a unique 0 less than x star less than a half, so that's period 2. So there's my x star somewhere. This is not to scale. There's f of x star. And I take y just to be this bit. Don't know what I drew that for. Don't know if that's going to delete everything. No, it's good. Right. So y is here to here. So I take y to be x star, f of x star. And it turns out that it's kind of well known and easy to check that this, if you take the first return map to this set y, it's a mixing Gibbs-Markov map. So everything I talked about applies. And again, I want to emphasize that I've just mentioned 2 examples, one with 1 neutral fixed point, one with 2, but it works for any number of neutral fixed points, and the branches don't have to be full. So Thaler kind of studied generally the case where the branches are full, but Brodens-Freimuller in 2 papers in 1998 and 2000 showed how to deal with the general case, and everything works just the same. So there's no restrictions on this result. Okay, so I have a feeling that something was missing somewhere. I think this theorem I stated about the Krickeberg mixing, there's actually a constant here. So I should have mentioned that there's some constant that depends on alpha, but also some constant that depends on the dynamics, and that would depend B1 and B2. B1 and B2 during the neutral fixed point will come into this value C. But it's independent. But of course, once you fix the C, just depends on the dynamics, and then this thing works for all V and W that are in the nice smooth class. So, any questions about Krickeberg mixing? All right. So now I want to talk briefly about global local mixing. So one problem with Krickeberg mixing, or one big restriction, is of course, if the right-hand side is going to be well defined, then we have to assume that V and W are both integrable, which is a perfectly reasonable, very soft assumption in the finite measure case. But in the infinite measure case, it means that, for example, continuous functions are not necessarily going to be integrable. Constant functions are not integrable. So Marco Lenci in 2010 tried to introduce somewhat more reasonable classes of observables. So this was the global local mixing. And sort of, if we would say, if V is, roughly speaking, if V is in L1, that will be local. And if V is not in P for P finite, then we might say that's global. So roughly speaking, we want to allow the possibilities that the V's might not be finite, finite integrable class. So what we're going to do here is I'm going to keep that V is in L1, but I'm going to allow W to be not in L1, and actually W is going to be just in L infinity, but satisfying some extra assumptions. And what we want now is the integral of VW composed, so this is now G, composed with f to the n d mu. So I'm going to now call WG. So G is going to stand for global. And integral of VG composed with f to the n d mu is going to converge to integral of V, but some quantity that I'll call G bar. That should be d mu. So I still want this correlation function to decay to something. On the right-hand side, we're going to get the mean integral of V, that was the integral function, but times some G bar, which depends on G, and no normalization constant. So there are no ANs anymore. And so here, V obviously is in L1. Already G is in L infinity. And you want some kind of assumption that says the integral of Zm G d mu over integral Zm, oops, yeah, measure of Zm converges to G bar, and you have to choose the Zms in some reasonable way. But the idea is that Zms are going to be things that have finite measure, and they're going to get bigger and bigger. So they're going to be nested, and eventually they're going to exhaust the space. If you look at the measure of the complement of the union of the Zms, that goes to 0 as m goes to infinity. And you want to have some G bar on the right-hand side that's the limit of this. And in that case, this would be called a global observable. So this is, roughly speaking, the definition of a global observable in Markov-Lenci's theory. And then what you want to prove is that this integral V, oh, can't actually see anything I'm doing, so for some reason I'm writing in green. I have no idea why I'm writing in green, but what we want is that this holds for all of these type of observables, but except they haven't been precise about what the G's are yet, because to be precise, you have to say what the Zms are. So in the case of a intermittent map, with neutral fixed points psi1, psi2, I assume that I've got D neutral fixed points, and then what we will say, we'll say that G is global if there exists a G bar such that the over x minus the epsilon of psi1 union the epsilon of psi d of G d mu over the measure of x minus that union converges to G bar as epsilon goes to 0. So that's our definition of that. That's kind of the natural definition of global observable in the case of intermittent maps. You just all of the infinite measure is kind of focused at the neutral fixed point. So we remove small neighborhoods of all the neutral fixed points. That gives us a finite measure set. Integrate G over the finite measure set, divide by the finite measure set, and then let epsilon go to 0. And that should convert to G bar. So that's the definition of G being a global observable. That's the definition. And then what we proved is, so this is the theorem of Doug and myself last year, is that indeed measure of that the integral of V G composed of f to the n d mu converges to integral of f d mu G bar for all V in L1 and for all G in L infinity that satisfied that definition of global observable. That's the theorem. And time is it? 12:35. Okay, so I'm probably going to finish before. So I should say there were some special cases. So the case d equals 1 was considered by Bonanno, Guiletti, and Lenci in 2018, and then there was also a paper later by Bonanno and Lenci in 2021, and these papers were restricted to the case where there was one neutral fixed point, and there were various other restrictions. For example, I think for LSV, the borderline case alpha equals 1 didn't quite work so well, and there were other restrictions on what kind of intermittent maps you could work with. But our claim is that this theorem works for all intermittent maps because they all have this inducing scheme by Roden-Steinmuller, and so everything should be good. So that's the theorem in the context, and I just wanted to mention some easy steps at the beginning of the proof. So there's some easy things. Is first of all, without loss of generality, G bar is equal to 0. So this just follows from you can just subtract the G bar and you get to what's called the centered case where G bar is equal to 0. The next thing, which is not so obvious, but this is already in the paper by Bonanno and Lenci. Is that without loss of generality, V is anything I like. I can take V to be any L1 function I like. Once you've got it, as a consequence of they showed that as a consequence of exactness, if you had it for one L1 function, you had it for all L1 functions. So I'm just going to always assume I've got this nice inducing space and just take V to be the indicator function on that set Y. And so I need to show we're required to prove the integral of on Y of G composed of F to the N d mu to 0 for all centered global G. So we just show that for every L infinity function G that satisfied that definition of being a global observable with G bar equal to 0, then we just have to show that its integral of its iterates on Y converges to 0. So that's two things that come for free. That's already well known since 2021, if not. I mean, it was already in their earlier papers, but it was made completely general in this paper. And then, our point of view is what we decided to do. The first main step of our strategy was to say, well, we already know that all of these things are Krickeberg mixing, because that was shown by Grisel and myself and Dalia back all that time before. So So the first step in Cope's and myself, I guess, is that we show that we assume Krickeberg mixing. So we have a general framework, but in particular, Krickeberg mixing is satisfied for the intermittent map. So this is our assumption. And then we show that it reduces to be required to prove that the sum J equals 0 to N, AM minus J inverse. These are the same. So we got those constants with ANs that were defined before. We called it in the borderline case alpha equals 1, AN is log n, and in the alpha is less than 1, AN is n to the 1 minus alpha. So we got these constants, and then integral of y, 1 tau greater than j, composed with f to the j, d mu converges to 0. So the claim is that the whole thing boils down to this kind of convolution between the inverses of the sequences of ANs and this sequence of functions where we look at G composed of f to the j, but no longer on the whole of y, but just on the set where tau was large. And this is just from the general framework that you've got this inducing set, and you've got the taus, the measure of tau greater than n is 1 over n to the alpha, as before, and that the capital F defines something that's Krickeberg mixing. Under those assumptions, you get down to this. And then you've got to start working. But that's the first 3 steps. That G bar is 0, that V is indicator function of Y, Krickeberg mixing gets you down to this. And that's when you have. So I think that's really all I had to say. So that's probably much too fast and incomprehensible. I don't want to online talks. So thanks.
Okay, thank you. So we have a lot of time for people asking questions or making comments about talk.
I have a question, if I may. I want to thank Ian for the beautiful talk and for accepting the invitation. I was puzzled ever since the paper by you and Doug came out about this generality in which you treat the case of multiple fixed points. So, and let's say what I call the large box, the set that you exhaust out to cover the entire reference space, in this case the interval, is the complement of neighborhoods of radius epsilon of the indifferent fixed points. And epsilon seems to be the same for all of them, disregarding what kind of singularity you have there, what kind of, I mean, I understand you have the same alpha in every one of them, so you have the same order, but in the constant, I mean, this epsilon seems to be independent of the constant. And this is very puzzling to me. And I mean, I can kind of think of counterexamples, in fact, actually. It seems strange. So unless I'm missing some hypothesis which I didn't catch while reading your paper, which I didn't read carefully enough in the proofs, but I looked for the proof of this part, and you say it's an easy calculation. Can you enlighten me on this part? Why would you not care about, epsilon is the same for every indifferent fixed point?
I certainly not be able to remember. I heard a rumor that there was something you were unhappy about, but we weren't given any advance notice as to what the rumor was. So it's kind of hard to put us on the spot and expect us just to answer it. Certainly, if that's the bit you're concerned about, we will look at it this afternoon and work it out. Okay.
Okay. I was gonna give you some ideas on how to construct, possibly, unless I'm missing something, a counterexample, but absolutely, I mean, you can actually move this to a private conversation. That would be probably easier.
So so the issue is with having the same epsilon at each.
Yes.
Point?
Yes. I don't expect the order to be different, but maybe a constant in front of epsilon seems reasonable. That you don't have, though.
Okay. Yes. Well, okay. Well, maybe we can have a look at this.
Yes.
Okay. So thanks. Are there more other questions or comments? Maybe more general about the ideas, I think, the definitions. The talk also.
Sorry, are there quantitative versions of the Krickeberg mixing results that you have, or Wesel has, or?
In the paper in 2012 of Daly and myself, there were quantitative results, but only for the so again, if I go backwards, So once we started generalizing it to things that saw the whole of the interval, then the quantitative results went away. But in the main setup, where you fix an interval that's bounded away from zero and work with observables that are supported on there, and with the first function being BV or holder, then in the case of the intermittent maps, we got error terms. But they were very specific to the intermittent map. So the fact that the density is nicely behaved and everything. So in nice situations, if you work with the very restricted classes of observables, you can do more. My feeling is that in the work with Doug, I could be wrong, but my feeling in the work with Doug is that we kind of have to push the supports of one of the observable W, which is now G. We have to support it. We have to push it further and further. And I would expect you would lose, if you want to prove the global local mixing, I would expect those error terms, the good error terms to go away. I could be wrong, but my guess is that you can't get convergence rates in global local, and you can't get convergent rates in the Krickeberg unless you really restrict.
Yeah, no, assuming some regularity, some extra regularity on the functions, of course. I didn't.
So the V, of course, we just take to indicate a function of y. That's as good as you. That's perfect. But you'd have to assume a lot more on the W or the G to get something. And this I think this first step that we took over here is probably already going to mess things up a bit. this step is going to have to be refined significantly. The error rates.
Thanks.
Other questions? Okay, so if not, we have to thank Ian again for the talk. Thanks. And then we can have a break, and we resume a few minutes before 5 for Doug's talk.
Okay. Excellent.
Okay, so we start again with our second talk of the day. So Douglas Coates from the Universidade Federal de Rio de Janeiro will talk about global local mixing for intermittent maps.
Thank you very much. Thank you for the invitation. I'm going to carry on from Ian's talk and try and some of the main steps of the proof of this global local mixing result. I've got 30 minutes. Is that correct? Perfect. Okay, so I will say what I can in that half an hour. I'm going to start off by saying something more about this inducing scheme to give a little bit of extra structure. So I'm going to fix just this one example with two neutral fixed points. But as Ian was saying, this sort of algorithm, this inducing scheme can be generalized, has been generalized to far more general settings by Roland Zweimüller. So we have these two neutral fixed points, and we were taking this unique orbit of period 2, which I think Ian called x star, and this is f of x star, and this is my interval. Okay, and we had this, we mentioned that it was possible to show that the measure of tau being bigger than n was asymptotic to some constant over n to the alpha, where tau is the first return time to y. So this is, let me make this clear now. So I'm going to put mu y for the measure restricted to y. So this is because I want to think about also how long it takes points to hit y from elsewhere. So this is okay. So I just wanted to point out that you have the following sort of structure. So if we look at a point inside y, if it's somewhere here, the image of this set is exactly this half, right? By definition. In fact, it's just this part, right? So the image of this interval. So if I'm over here, I end up somewhere close to this fixed point. I spend some time there. I bounce around until I end up back inside y. And then when I end up back inside y, I can end up anywhere in this interval. And I repeat the process. So an important thing about the choice of this interval is that I can only visit the neighborhood of one neutral fixed point before I return. Okay, I can't jump from this interval to this interval without first passing through y. So this is an important part of this choice. So I'm going to call this set, it's a bit unfortunate to have lots of, I'm going to call this x1 and this set x2 with a subscript. And okay. And I can also look at how long it takes. Okay. So I want to divide partition x1. I'm going to write xn12 to be the points inside x12 such that they first hit y in n steps. Okay, so these are the points inside the respective x1 and x2 that will take n iterates to hit y. So by doing this, you end up partitioning these sets in a way that accumulate at the neutral fixed points. And this would be x11, x12, and so on. Okay. One can check that in this setting, so something that we will use is that the measure of one of these xn 1, 2s will be asymptotic to some c1 or 2 n to the minus alpha. Okay, sorry, this is an alpha plus this is right, okay. Fine. Okay, so what my definition is of I'm going to be a bit more precise about what I mean by global observable. So I'm going to say that G is global if the integral of the union from 1 to n of the xi g d mu over the union over just the measure of this set is converging. So this is G in L infinity is global if there exists a G bar such that this converges. Okay. Fine. And I'm now going to try and, so this, okay, so what I want to have a look at now is trying to characterize this condition in a way that is slightly easier to handle. So if we remember from Ian's talk, it was enough to consider just the case that G bar is 0. Okay. So the next step I'd like to show is saying that the following lemma is that G is centered and global, meaning that this thing is converging to 0. If and only if the limit as n goes to infinity of an minus 1, the sum from I equals 1 to n of I to the alpha G bar I equals 0, where this G bar I is just the sort of local average of this function on the xn's. So this is on, it's like this. Okay. Again, this an was as before. This is the sequence n to the 1 minus alpha, or the logarithm of n if in the case that alpha is equal to 1. There's some characterization of being global. So this is not too hard to see. So I'm going to call just xn, I'm going to define to be just the union of these two parts. So this is like this. Okay, these are the points that are near one of the two fixed points and take n iterates to hit y. And if I look at this thing here, so this is what was in the top, in the numerator of my definition of being global. This is just the sum of the measure of the xi's times these local averages. And here we can use the fact that we know how quickly these xi are decaying. So this is some constant I to the minus alpha G bar I plus something which is the little o of the sum. Well, let me write it like this, so just like equal to, sorry, like and finally, because we know what these because we know the measures of these xi's, we know in fact that the measure of the union of these things is in fact like an. Okay, some constant times an, some different constant times an. Okay, so putting these two things together, I can't scroll. Sorry. Okay, right. Putting these two things together, I end up with saying that this thing is equal to this leading term plus something that is the little o of an. Okay, and that is exactly the so if this divided by this measure is going to 0, that is giving me precisely this condition here. Okay, so it's giving me some equivalent condition for that is hopefully slightly easier to work with than the definition. Okay, so now our aim is reduced to the following. We assume that G is such that this condition holds, so the limit of an minus 1 of this sum is 0, and we want to show that this implies that the g y f to the j d mu is converging to 0, which by this Krickeberg mixing and what Ian mentioned, this is the same as showing that the sum from j equals 0, an minus j tau y1 tau bigger than j of g times f to the j d mu. And we want to show that this first condition implies that this thing converges to 0. Okay, so if you stare at this long enough, this suggests dividing into two cases. The case where this function g is locally constant on these intervals xi, and the case where it is mean 0. Okay, so I can always decompose this g into the sum of two functions, one that is constant on these intervals xi and one where it's mean 0. So first, let's suppose that g is piecewise constant on the x1n union xn2. Okay, so this means, so this was my xn. This means that g restricted to xn is going to be exactly equal to this local average. Okay, and I know that now I've just got a real sequence of real numbers, property.
So I'm a bit confused. Are you assuming that g is constant on the whole of xn or on two pieces of xn separately?
On the whole of xn, or on each piece of xn, sorry. Thank you. Right. Okay, so yes, I want to assume that g is constant on each piece of the xn, so that g restricted to xn1, 2 is just a constant, and this is going to be equal to what I will call g bar I1, 2. Okay, and this previous condition that I have here, where has it gone? Okay, reduces. Okay, so I've got this function that is piecewise constant on these intervals xn, and I've got a condition now about a sequence of real numbers being summed against this I to the alpha going to 0. Okay, so this is just something that this reduces the problem to just a problem about a series of real numbers. You're saying, I know I've got a sequence of real numbers with this property, and I need to prove that that same sequence of real numbers is satisfying this. Okay, so maybe I should be a bit more precise here that Okay, I've made a bit of a mess here. G composed with f to the n. This is the thing that we wanted to show is going to 0. This, by what Ian said, is this object here. Okay. Now I can decompose this into the sum of I equaling 1 to infinity of sum of k equaling 1, 2 of the intervals tau x in such that tau of x is equal to I plus j. Well, let me first do it like this, just like this. G composed with f to the j d mu. Okay, now the point is that I've made a real mess here, but this set here, these are the set of points in Y that return in time I plus j. I'm going to call this set yi plus j. Yi plus j is being mapped bijectively by f to the j into the set of points in the complement of y that are in I iterates. So they're getting mapped into these xi's. And I can break up each one of those into the two parts, the ones that go near one fixed point and the ones that go near the other. Okay, so after doing after using the fact that this thing here is piecewise constant, this whole thing here, which I will just try and well, maybe I'll just try and say with words. Okay, but so you have this f to the j is this bijection from the points in y that return in time I plus j. It's getting mapped bijectively into the points in the complement that are hitting exactly in time I. You can divide those up into two pieces. The xi 1 and 2. Okay, so what you're seeing in this integral is really just this, the sum of g bar I at 1 and 2 scaled appropriately. So this reduces the problem of showing that this integral, the iterates of g composed with f to the n going to 0 to proving that certain series is converging to 0 in the limit as n goes to infinity. Okay. That's all I want to say about that part. Okay, and I'm probably going to say something equally confusing now about the other case, which is when you have mean 0. Okay, so now suppose that the integral over xn(1,2) of g d mu is 0. Okay, so we can always decompose into this case where it's a constant plus something of mean 0. So I'm going to suppose straight away that that this is now the case. Okay, so we had the set y I plus j 1, 2 is being mapped after j iterates into x I 1, 2. Okay, recall that this is the set where x in y such that tau of x is equal to I plus j. And this was the set of x in x, y, such that tau of x is equal to I. Okay. Now this is happening in some smooth way, right? So which is apart from being, so what I want to say here is that it turns out that if I consider the Jacobian of this map, so if I look at the Jacobian of this map, f to the j, that is taking this piece to this piece here, this works out to be roughly piecewise constant in some very strong way. So if I define jij to be the derivative of this map, so this is exactly the derivative of f to the j restricted to this interval, star mu, okay, d mu xi on 2. This Jacobian turns out to be roughly piecewise constant, and this gets better as I and j go to infinity in a very strong way. Okay, and one can calculate this for intermittent maps just using the formula for the invariant measure that comes from the inducing scheme. By you've got this inducing scheme and you know that you have some nice measure for your Gibbs-Markov map, and if you want to pull this to a measure for your original system, you sort of have to chop it up and spread it out, and this is by this Kakutani's formula. This is very standard. You look at that your invariant measure will have this form. Okay, and because for these intermittent maps with these nice expansions, you can calculate, you have these very nice estimates for how this measure is behaving near the intermittent fixed points. And because this term here looks like just one term in this sum divided by the whole sum, you can get a very good approximation for this Jacobian. And it works out that it is roughly piecewise constant in some very strong way. Okay. So then when you're looking at this, again, you're going back to this reduction that we got from this Krickeberg mixing. You've got this G composed with f to the j d mu that you're trying to show converges. We know that this is an minus j to the minus 1 sum from I equals 1 to infinity of this. Okay, you can then divide up this part here into the sum of the two pieces. Where your map is nice. Okay. So let me just work with one of these, as it's the same the other way around. If I look at one of these integrals here, I just do a change of variables to introduce the Jacobian. This becomes the integral over xi1 g multiplied by this Jacobian. And because this is roughly a constant, and because g is of mean 0 on xi1 by assumption, I can add and subtract that constant. So okay, so this is where I was. So I can write this as, in fact, Jij, this Jacobian, minus the thing is asymptotically equal to, in some strong way, plus 0, right? Because this other term here, Cji g d mu on xi, this is 0 by assumption, right? Because this g was so then you're in a situation where this object here is going to 0 in some strong and controllable way as you make j and I larger. And when you plug that back into this formula, you can see it works out that the error terms are enough to make this whole thing go to 0. Okay, so that's all I wanted to say, really. So the proof divides into these two parts where you have the piecewise constant case and the piecewise mean zero case. Piecewise constant case you reduce to a problem about a series. The problem just in real analysis using the definition of global observable. And the piecewise constant case, the piecewise mean zero case, you treat by showing that this Jacobian is asymptotically like a constant. Okay, that's all I wanted to say. Sorry if that was a bit fast and a bit confused, but yeah.
No, not at all. Thanks a lot. So again, we have time for questions or comments. Questions? Maybe I can ask you about the case where the order of infinities are different, the two fixed points. So are there ideas of adapting this proof to that case?
So when you have two different tangencies, the thing that this proof sees is the tail of the return time. Okay, so as Ian was saying, that we had this general setup where if you have this inducing scheme, and the main thing we're assuming is that this return time has a certain tail. Now, if you're in a case where this is an alpha 1 and this is an alpha 2, only one of them is going to come into the tail. Only the largest one is going to come into play. So, in fact, this is treated in this situation. So you can have whatever different orders you like. This alpha is corresponding to the largest alpha, the stickiest alpha, and that's all. Does that make sense?
Yeah, sure.
Yeah.
So okay.
Yeah, so I mean the alpha just corresponds to the stickiest alpha that you see in all of your fixed points.
Okay, so are there other questions? Okay, maybe not. So we thank Doug again. Thanks. And thank you to both the speaker, and bye-bye to everybody.